Hi everyone, welcome to our first lecture back from spring break. I would like to point out I'm still in my bathrobe. I think that's pretty awesome, and I still have a sparkle pen. So let's try this, let's do it. One of the things I wanted to do right when you got back from spring break was help you with your cheat sheet. Something that's really helpful in organizing all of this Unit 3 is taking a look at all of our reactions and trying somehow to organize them. Remember, this isn't a memorized course, so you don't want just a list of reactions you put on flashcards and you memorize them. This is a problem-solving course. We're going to have synthesis on this test. We're going to have IR on this test. There's all kinds of things on this test. So let's take your notes and let's organize them. So if you want to hit pause on this for a second, grab your Unit 3 notes, grab the 5 reactions that we're doing, and I'm going to give a basic skeleton just to give you ideas of how to organize, but I'm not going to write everything in there. So please don't make this your cheat sheet. This is just giving you ideas, and I'd like you to do this first, because then we're going to take this and I'm going to work my way through a practice test, and we're going to review and work on some problems. So let's start to think about your cheat sheet and start to organize it first, and then we're going to go apply it and do some synthesis and do some fun stuff. So let's first start by thinking about all of our reactions. They actually flow like a really nice flow chart. One of the reasons we start Organic 1 with alkanes is that when you start with alkanes, in industry and in research, that is a very good place to start because they are a huge feedstock in the organic industry and in the pharmaceutical industry and any of the synthesis industry. They come from the petroleum industry. They are cheap and easy to buy. So an awful lot of synthesis starts there. If you want to target something, you have to have a place to start. And so I'm setting up this flow chart to help you study, but I'm also looking at it to help us in our next segue into synthesis. So we're going to start with alkanes. And what's beautiful is we learned only 2 reactions with our alkanes. So on this next test, your synthesis will always start with an alkane, and that's beautiful because you always know where to start. With our alkanes, we had 2 options. Remember, they were both radical halogenation, but they had some differences. Now we're going to start to view organic chemistry like playing chess. All of these pieces are like pieces on a chessboard. They all have rules. I will never break those rules. I may ask you to use those pieces in all kinds of different ways. That is what synthesis is. But I will not break the rules to those reactions. And where we get those rules is our mechanism. So you'll notice we drew mechanisms for all 5 of these reactions in this unit. Those mechanisms were to teach us the rules to those reactions. So for example, we had 2 different radical halogenations. The first one was chlorine and light. We drew the mechanism to that. We were able to draw out all of the different products that come from chlorine and light, and we saw that we had a whole different rule set. So if this is going to be our cheat sheet, let's mark this one as a mechanism. We definitely saw the mechanism. That should go on your cheat sheet. That will be on your test. And we also learned that our chlorine really is not choosy, and it can go anywhere. So let's also think about stereo. It was racemic. And remember, this is an awesome test question because we have to think about all of our stereoisomers. Holy crap. Remember, there were a lot. So if we picture chlorine, can't we actually add chlorine to all kinds of places for our cyclohexanes that I've drawn? Absolutely. We can add to primary. Remember, chlorine could go here. Chlorine could go secondary, chlorine could go tertiary, or our other secondaries. Oops. Oopsies. We could have a chlorine here. And then finally we could have tertiary and have chlorine there. And then what's awesome is let's tie back in stereo. Holy crap, do any of these have stereo centers? Absolutely. We have a nice stereo center here, here. We could have a cis and trans here, here. Okay, and we don't have stereo centers in those. So this is right where we ended with our radical halogenation. This is a great way to make an alkyl halide, and our alkyl halides are useful in synthesis because now we have, a leaving group. Okay, so we had rules to radical halogenation. If you use chlorine in your synthesis, you got to put it everywhere. It's the only way you can get to some of those substrates with chlorine everywhere. And we also had a nightmare of our stereoisomers, right? We could get a lot. In fact, if we just add up total here, oh, we have the possibility of 4. That doesn't mean we have that many. That just means they're possible. So just out of this reaction, we have how many? 8, 12, 13, 14. Okay, so we have at least 14 different products in chlorine and light. So it's advantageous if you want to get to something like this compound, okay, or this compound, but really to a synthetic chemist, this one really kind of sucks because you have so many products. So what was our other alternative? The other one was bromine and light. Okay. So what was the, something's talking to me, y'all. I'm so sorry. I think Alexa's talking to me. So in this one, what was the advantage to using bromine? Wait for it. Only, that's way too dark, y'all. Way too dark. So what was the advantage to this one? Our bromine can only go in that one spot. Let's try and find a thin tip here. Let's try a pencil instead. Let's see if that's better. Okay. Wow, that super sucks. Welcome to my first video. Okay, let's try this again. Let's go thin. Okay, our bromine can only go there. So synthetic-wise, this is awesome because now you've got a really good leaving group and you're going to make the most hindered alkyl halide. So synthetic-wise, that one's usually pretty good. We really like that one. Okay. So now let's take a look at what can we do with those. We started with the radical halogenation on purpose because radical halogenation was now how we're about to do a whole lot of other reactions. So this is where the flow chart comes in. Picture a tree with a whole lot of roots. Now that you have a leaving group, now we can do stuff with it. So let's take our document, let's move it down just a little bit. And let's start with the tertiary. What are our options? So we actually saw 4 different reactions with an alkyl halide. We had an SN2, now we saw in our notes SN2 does not happen on a tertiary. So our flowchart just got a little bit easier, didn't it? So what are the other 2 options? We had an E2. Okay, E2s definitely happen on tertiary. And then we had an SN1 E1, and they typically come together. So how do you spot those, and what are the reaction conditions for those? This is something you need to put in your cheat sheet that I'm not just going to give away for free. And so one of the things you want here is the actual conditions for an E2. So what kind of conditions do you need on your E2? You need a base. So we've got a whole set of rules here for our base. Remember, size matters. And antiperiplanar. These are things that should go in your cheat sheet for sure. What does that mean for base? Well, let's say we have a small base. We're going to make this alkene. If we have a large base, we're going to make this one. So that's awesome. On an E2, we have selectivity. So in synthesis, you're going to want to use that. If you need to make an alkene here, you need this small base. If you want to make an alkene here, you need the large base. That's perfect. Awesome. All right, what about an SN1 E1? We had some rules here too. We had some rules that if it, oh wait, this is tertiary, those are the best carbocations. That's why that can happen. That's why that works. So we always get a combination of our SN1 product and our E1 product. SN1, we add our nucleophile there. Our E1, we make the most stable alkene. Now, all of these things, you need to add detail. You need to add detail. This should turn into what you think about on your cheat sheet. How are you going to spot an SN1 E1? What did we learn for that reaction? We had only solvent. It was polar, protic, and our solvent was our nucleophile. Okay. With our E2, we had our base, our large base, LDA, our small base, anything else. Okay. And how did we spot that? We had on our cheat sheet a base list. That is on your handout from lecture. We had bases versus nucleophiles. All right, so then, we can do a lot with the tertiary. How about a primary? So if we take a primary alkyl halide, could we do an SN2 reaction? Absolutely. That's awesome. And how do you know? You add your nucleophile. And what kind of solvent did we have? Polar, aprotic. And you had nucleophiles on your list. That should be on your cheat sheet for sure. That was something that we handed out in class, our solvents and our nucleophiles. So then with a primary, could we do an E1 SN1? No. Nope. We could handle the SN2. Those were awesome. But E1, SN1 don't happen. What about an E2? Absolutely. Our E2 works really well with a primary. So which product are you going to make? Only that one. So that could be with any base. And why only that one? You only have one set of beta hydrogens. Let's mark that again. Only one beta hydrogen. So all of these are rules that you need to take this idea and make it pretty. Okay? And now let's tackle the worst one out of all of this. So of course it's my favorite and it will be on everything. And that is our secondary alkyl halide. Our secondary alkyl halides do everything. So let's write a nice list for our secondary for all of our reactions since they do everything that we've talked about. All right, can we do an SN2 reaction? Absolutely. We can totally do an SN2 reaction on a secondary alkyl halide. And where do we substitute on that halide? Wherever that halogen is, that is where you end up adding your nucleophile. Okay. How do you recognize this? Let's take a minute and let's spell out all 4 reactions. This is something you should organize and make look pretty on your cheat sheet. Remember, we've got 4 things to consider for all of these reactions. The first one is our nucleophile, our electrophile, solvent, and our leaving group. Okay. So for an SN2, our nucleophile is coming from that list. I gave you a list of really good nucleophiles. That should be on your cheat sheet. Okay, our electrophile, that is always connected to our leaving group. These 2 are connected to each other. Our electrophile in this case is secondary. Okay, secondary works, primary works, tertiary does not. Our solvent, polar, aprotic. Our leaving group in this case, chlorine or bromine. So if I were taking this next test, I would list all 4 of these things with each of my reactions. So for a secondary alkyl halide, you can do an SN2. It has to come from the list. And here's what's specific. It cannot be a base. Okay? That is what's tricky about an SN2. It can only be a nucleophile, not a base. So for example, sodium chloride, yes, awesome. Sodium hydroxide, no. And what is it going to do instead? An E2. So I think that's one of the trickiest things to think about for a secondary in an SN2 is that you have to compare your base list to your nucleophile list. You have to compare them, put that in your cheat sheet. You have a competition there. Okay. So let's keep that in mind for secondary SN2. And then I'm going to take a second and erase and give myself some more space. And then we're going to tackle our E2. All right, let's do the same thing for our E2. Can an E2 happen on a secondary? Absolutely. Only this is what's awesome. The first thing we did was discuss size matters. So if we have a small base, we are going to make the most stable alkene. What could be a small base? How would you recognize it? Sodium hydroxide and water. Sodium methoxide, methanol. They typically match. They are on that list I handed out in class as bases, not as nucleophiles. So you had a list from class that gave you this as a base, not a nucleophile. So on a secondary, you will have the E2 reaction, not the SN2 reaction. Okay. So then we only had one large base, so that's awesome because you can spot that sucker. Let's put it in Sparkle Pen. This is so much fun. How do we spot that? It is my favorite base ever. It is nice and modern. That is LDA, and we put that with its matching DIPA. And that is our lithium diisopropylamine, and diisopropylamine is our solvent. So let's put that in there. Why does size matter? Remember, we have 2 different sets of beta hydrogens on a secondary alkyl halide. If this is our alkyl halide, you have a beta hydrogen here or here. Size matters. So in your small, you can take that beta hydrogen right here with your small base. But with your large base, you're going to go for the easier hydrogen. So what compound does that make for us then? That is going to give us, I think I changed from my blue. That is going to give us this one. Okay. So size matters with those beta hydrogens. And then just wait for it. It gets even more fun. Shut the front door. I love it because we don't have to stop there. What happens? What? The plot thickens. What if you take this substrate and you have stereocenters? Dun, dun, dun. It's like a cliffhanger. Now we need to add to it not just size matters, but also come on, y'all, I'm still getting used to this. Okay, we need to add anti-periplanar. So if you're in a cyclohexane, this is awesome. You guessed it. We add a chair, and you need your leaving group and your beta hydrogen axial. Okay. If you are not in a cyclohexane and you are in something crazy with stereocenters like this, both of which are in your homework, now you need a Newman projection. Remember, you need your leaving group and your beta hydrogen, anti-periplanar. So for sure, those will be on your test. Those are some of my favorites. You have to distinguish several different things. First, you have to figure out that you have a base and not a nucleophile. Then you need to check your size. Then you need to check your anti-periplanar. So should you bust out your model set on this next test? Absolutely. Will I try to draw them funny? Absolutely. It'll be awesome. So now our E2 is actually quite complicated on our secondary. So I'm going to pause for a second and do some erasing. But all of this needs to make sense and be nice and concise on your cheat sheet. And then let's tackle an SN1 E1. So then what can we do next? Well, what if we have a tertiary? I'm sorry, that's stupid. What if we have our secondary? Can we do an SN1 or an E1? Yes. So in fact, secondary, we can do everything. How do you recognize SN1, E1? So let's put our leaving group here again. Secondary. What if our reaction conditions had simply water on there? Water is not negative. It is nice and neutral. And you don't have a solvent, or your solvent is your nucleophile. They are the same thing. So you have only one reagent. Your solvent is your nucleophile. Okay. So why do we give a crap? What does that mean? That means, this is going to be so much fun. This means that we actually get a nice competition. It means mechanism-wise, your leaving group leaves first. And we make a carbocation. Now, shut the front door, stop right there. When you make a secondary carbocation, remember we had some rules here. They can rearrange. Now, you'll only see this in a mechanism. I won't expect you to predict the rearrangement. I will ask it in a mechanism question. You want to avoid SN1, E1 if you can in synthesis because of this rearrangement. You always rearrange to something better. And that's the first thing. And we can move a bond to a carbon or a bond to a hydrogen. Those are our rules. So in this case, we saw this one right at the end of lecture before spring break. What can we literally rearrange to? Well, we can move a hydrogen and fill in that space. these electrons fill in, and now we've got a tertiary carbocation. Would that happen? Yes. And then what would our product be? That alcohol. Okay. So our secondary carbocations will show up in our mechanism questions. You can substitute or eliminate. So let's draw that in on our products. You can end up making this alcohol, or you could end up making the alkene. You're going to have a competition between your SN1 and your E1. Okay, so I hope I've at least given you some things to think about for your cheat sheet. You have a whole lot of information on this next test, and you need to find a way to organize it. Part of it, hopefully you watched the instruction video online, and one of the things you saw in there that I'm still going to require a cheat sheet. I would really like you to still take some of these ideas and make a cheat sheet. It's an awful lot of information, and if you can coordinate that and organize it, your life gets a whole lot easier. So stay tuned. I'm going to have some more videos with some actual problems, and let's take our flowchart and apply it.